Hi, this is an example problem from Chapter 1 about a charged particle in a magnetic field. Pause for a moment to read the question. So in this particular problem, they've given us an image of the particle here, and we see that it's got a velocity vector here in one direction. There's also a magnetic field B and an electric field E in the space, and at the position it's at, we can see the B field is up in the direction of the positive z-axis. The E field points in the direction of the minus x-axis, and so we see a picture of this three-dimensional coordinate system that we use to represent things. In your problem, for the peer review problem, you're going to have to go ahead and draw a picture of the charge. The field is already shown, the field lines, and you'll have to identify the different vectors that act, the velocity vector, the magnetic field vector that act on the charge. So to start this problem, this is a problem where we're going to calculate the magnetic force that is exerted on that charge due to the fact that it's immersed in a magnetic field. We're also going to need to figure out what is the force exerted on the charge due to the electric field. But let's focus first on the magnetic force. So we know that the magnitude of the magnetic force Fb that acts on a charge, it's moving in a magnetic field, it's given by the equation. It's the magnitude of the charge times the speed or magnitude of the velocity times the magnitude of the magnetic field at that position multiplied by the sine of the angle between v vector and b vector. Now in this problem we can see that the angle here between v and b, it's a right angle. So this is going to be 90 here. And if we go ahead and put in some values to calculate Fb, we are going to get, for the charge magnitude, we see it's negative, right? That's okay, we're just going to put in the charge magnitude, so 2.8 times 10 to the minus 6 coulombs. The speed is given to us, 4.8 times 10 to the 6th meters per second, so it's zipping along pretty quick. The magnetic field magnitude is given to us, 33.5 times 10 to the minus 6 Tesla. And sine of 90 degrees, well, that's going to be equal to 1. And just to check that I'm in SI units, coulombs, meters per second, Tesla, good. That means I'm going to end up with newtons of force here when I calculate this. That comes out to 4.50 times 10 to the minus 4th newtons. And so I just point out that this orientation perpendicular the velocity to the magnetic field, that's when we get the max magnitude of Fb, and that's again because sine of 90 is equal to 1. So we just got the magnitude of Fb. Now we want to figure out the direction, and for that we're going to have to use what is called the right-hand rule, number 1. So to determine the direction, I brought in a little picture of the right-hand rule. Make sure it's your right hand. And the fingers point in the direction of the magnetic field vector. The thumb points in the direction of the velocity vector. And the palm points in the direction that the force is exerted on the particle. So it's a strange way that the force is exerted for a moving particle where there's a magnetic field in space. So to go ahead and overlay this in a sense, right, you can kind of see the B is up, the V is in the direction of plus y-axis, and the force, if it were a positive charge, it would point in the positive x direction, as you can see. However, this guy here is a negative charge. As we've learned so far in electricity and magnetism, everything is opposite for negative charges. So in reality, the force that is exerted on the negative charge here, it's not going to be in the plus x direction, so it's not this. It's actually going to go like this. Exactly opposite. So here's your Fb in that direction. And so we can say directed in minus x. And if all we were asked for was the magnetic force, we would be done at this point. However, they want us to get the net force, and we know that electric fields also exert forces on charged particles, and so we're going to go ahead and do that one next. Let me clean up the picture again real quick. All right, so Now we're going to go ahead and figure out the electric force. Well, the electric force is much simpler. To determine the magnitude of the electric force that acts on the charge, we're going to go ahead and just multiply the magnitude of the charge times the magnitude of the electric field. Charge magnitude 2.8 times 10 to the minus 6 coulombs, and the electric field strength is given 123 newtons per coulomb, which gives a force magnitude 3.44 times 10 to the minus 4th newtons. So here's our magnitude of the electric force exerted on the charge. And again, this is negative. So we know that a positive charge experiences a electric force that points in the direction of the electric field. Because this is a negative charge, the force is going to point in the opposite direction. So the electric force is going to go in this direction. And that's going to be a little bit, oh, let's draw it again here. That's going to be a little bit shorter than the magnetic force because of the numbers, right? I guess I can kind of go ahead and get rid of this for a second because this is not quite our final answer yet. But we've got the two forces here, your magnetic force. The electric force is directed towards the plus x-axis, right? And to get the net force, all we're going to do is add these two together. So F net, it's only going to be on the x-axis. We're going to have a positive value for Fe. So we're going to be adding these together, right? Fe plus Fb to get the total. Fe is going to be positive x, so we're going to put a positive 3.44 times 10 to the minus 4th newtons. And for the magnetic force, that one's in the minus x direction, negative 4.5 times 10 to the minus 4th newtons. When we add these together, we get minus 1.06 times 10 to the minus 4th newtons. So there's the x component of that net force. The y, z components are both 0. And so that means that the magnitude of the net force, if we want to write this down, what's the magnitude of the net force? It's going to just be the absolute value of that value. So 1.06 times 10 to the minus 4th newtons. And there's our answer for this one.